65 million years ago, a colossal asteroid crashed into the Earth with unimaginable force, wiping out the dinosaurs and reshaping the history of life itself. For most of us, that cataclysm feels distant. A line in a textbook, a reminder of ancient times. But what if such an event wasn't confined to the distant past? What if the sky above us is still hiding silent killers? Every night, telescopes sweep across the heavens. They're not just searching for distant galaxies or beautiful nebulas. They're hunting for rocks, some small, some massive, that share our solar system. Thousands of asteroids orbit near Earth, and at any moment, one could find itself on a collision course with our planet. The frightening truth is that while science has made great strides in understanding these objects, our defenses are still frighteningly limited. An asteroid only 150 feet wide could flatten a city the size of New York. Larger ones could wipe out entire nations or civilizations. The last major impact of this scale occurred not millions of years ago, but just over a century in the remote wilderness of Siberia. That was the Tunguska Event. It flattened 60 million trees across 800 square miles. There was no crater, no warning, only a blinding flash and a shockwave felt hundreds of kilometers away. And it was only the beginning. Across deserts, ice sheets, and archaeological sites, evidence is mounting. Asteroid impacts have struck far more often and far more recently than most people realize. From a black layer of burned soil buried beneath the Ohio Earth to mammoth tusks peppered with high-velocity fragments in Alaska, clues point toward events that were sudden, violent, and world-altering. Some impacts were so intense they erased entire cultures without leaving an obvious crater. Meanwhile, new discoveries in space reveal an even more alarming picture. Astronomers have detected asteroids that will pass dangerously close to Earth in the coming years. One of them, named Apophis, is roughly 900 feet wide and will swing closer to Earth than some satellites. Had its orbit shifted just slightly, the consequences would have been catastrophic. At the same time, space missions are peering deeper into the solar system, uncovering extraordinary secrets about the places where these cosmic bullets are born. Around Saturn, a probe named Cassini has revealed chaotic rings made of billions of colliding particles, remnants of a violent solar system past. On Titan and Enceladus, worlds of ice and methane hint at conditions where life might exist, even as Earth faces threats from above. And beneath our feet, something else is changing. Earth's magnetic shield, the invisible barrier that protects us from deadly cosmic radiation, is weakening faster than expected. In the South Atlantic, a growing anomaly is allowing radiation to penetrate deeper toward the surface. Scientists warn that this may be a sign of a larger, global decline in the field. If that shield continues to fade, the consequences could mirror the fate of Mars, a once Earth-like world stripped of its atmosphere and left frozen. Taken together, these threads weave a single, unsettling question. What happens when the next asteroid comes, and our planet is less prepared than ever before? This is not a distant science fiction scenario. It is a scientific investigation into the very real dangers that have shaped our planet's past, influence its present, and may determine its future. Over the next chapters, we will follow the clues, from ancient impact sites on Earth to cutting-edge experiments at NASA, from the icy moons of Saturn to the weakening of Earth's magnetic shield. Each discovery brings us closer to understanding one simple truth. The sky has struck before. It will strike again. Part 1. A sudden flash in the sky. It began not with a warning, but with a flash. On a clear September night in 2007, villagers in the remote highlands of southern Peru looked up to see something strange cutting through the atmosphere. A glowing trail streaked across the sky, brighter than any meteor shower they had ever witnessed. Moments later, a deafening explosion shook the ground. Panic spread through the village of Caracas. Some thought it was a plane crash. Others believed they were under military attack. But when the dust cleared, what remained was neither aircraft nor weapon. It was a crater 50 feet wide, still steaming in the cold night air. Word spread quickly. Amateur videos surfaced online within hours. Grainy footage showed frightened residents pointing toward the smoke column rising from the ground. News stations replayed the same shaky clips, speculating about UFOs, falling satellites, or secret weapons tests. But among scientists, the incident triggered a very different reaction: disbelief. For decades, the prevailing assumption had been that small rocky asteroids, anything under a few meters across, would burn up in Earth's atmosphere long before reaching the surface. Objects only a few feet in diameter should never have the energy to make a crater like this. Yet the Peruvian site told a different story. Buildings over 150 feet away were damaged. Animals fled at the sound of the impact. Something small had hit the Earth with surprising force. Within days, one of the world's leading impact specialists, Dr. Peter Schultz from NASA's Ames Research Center, flew to Peru to investigate. When he arrived at the crater, he was stunned. "My first thought," he later recalled, was, "This shouldn't have happened." The crater was fresh, clean-edged, and surrounded by overturned soil. It had all the hallmarks of a high-speed impact, not an explosion or hoax. Eyewitnesses described the trajectory of the object as low and fast, entering from the south. Schultz began searching for physical fragments that could reveal the intruder's identity. Using magnets, he scoured the crater for metallic remnants. What he found was astonishing. Small, heavily deformed rock fragments, fractured in a pattern consistent with impacts at 3 to 4 miles per second, almost 5 times the speed of a rifle bullet. Back at NASA, Schultz analyzed the fragments under powerful microscopes. Combining their angle of entry with their deformation pattern, he calculated the object's size. It was between 3 and 6 feet across, no bigger than a small household table. By every standard model, such an asteroid should have disintegrated in the upper atmosphere. But this one didn't. Punched through, hit the ground, and made history. The implications were immediate and unsettling. If a rock this small could make it to the surface, what else could? How many more were out there? Untracked, unnoticed, waiting to surprise us. Scientists around the world began to re-examine their assumptions about atmospheric entry. The Caranca's impact revealed a blind spot in global monitoring systems. Current telescopes are optimized to detect larger, kilometer-sized near-Earth objects. Smaller asteroids, tens of feet wide, are far more numerous but incredibly difficult to detect. They can approach from the direction of the sun, hidden in its glare, and arrive with no warning. Caranca's was a warning shot. For the people who lived through it, the event was terrifying but short-lived. For the scientific community, it opened a new line of questioning. How vulnerable are we to the smallest asteroids, the ones that slip through undetected? And what happens if the next impact doesn't occur in a remote Peruvian highland, but over a dense urban center? The answer, as they would soon find out, lies in looking back through time, and deep into the layers of Earth's own history. Part 2, Echoes from the Past. The shock of Caranca's sent ripples far beyond Peru. Within weeks, geological teams, astronomers, and media outlets across multiple continents were revisiting their archives, searching for other anomalies that might have been overlooked. If a 3 to 6 foot object could breach Earth's atmospheric defenses, perhaps Caranca's was not an isolated fluke, but part of a larger, recurring pattern. The first clues came not from telescopes, but from the ground beneath our feet. Thousands of kilometers north, in the deserts of Arizona, lies a massive scar that has fascinated scientists for more than a century: Meteor Crater. It is nearly a mile wide and over 500 feet deep. For decades, its formation was a mystery. Only later did researchers determine that the crater was created by an asteroid roughly 130 feet in diameter, no bigger than a small jet plane. When it struck, it hurled 175 million tons of rock into the air. At first, the idea that something so small could produce such devastation seemed implausible. But the evidence was undeniable. The impact melted sandstone, produced temperatures of thousands of degrees, and obliterated everything within a 5-mile radius. If an object the size of a jet could flatten an area like that, scientists began to ask a chilling question. What if it struck New York City today? Simulations suggested that 80% of the city's population would be injured or killed almost instantly. Shock waves, heat, seismic activity, and collapsing buildings would radiate outward, overwhelming emergency systems. Unlike Hollywood's slow-motion catastrophes, a real impact would unfold in seconds. At Northern Arizona University, impact specialist Professor Ted Bunch had long studied the unique signatures of impact events. Among his most striking demonstrations was a simple comparison of desert sandstone. One sample remained intact. The other was shocked, heated and pressurized far beyond its natural state. The difference between the two was as clear as night and day. Bunch explained that the extreme heat and pressure of an asteroid strike leave physical fingerprints that last for millennia. Those fingerprints can reveal not only when but also how violently an event occurred. Meanwhile, thousands of miles away in Alaska, fossil hunters had been cataloging tusks of woolly mammoths when they noticed something peculiar. Many tusks were peppered with tiny, high-velocity particles, almost like shotgun pellets embedded in bone. The fragments dated back 34,000 years, a period during which the number of large mammals in the region mysteriously plummeted. At first, these markings were dismissed as random damage. But when Dr. Richard Firestone analyzed the particles, he found that they were rich in iron and nickel, the hallmark of meteorites. To prove the point, Firestone conducted a simple but powerful experiment. He shot mammoth tusks with a shotgun. The pellets bounced off harmlessly. The energy was nowhere near enough to replicate what was observed in the fossils. The only plausible explanation was that tiny fragments traveling at tens of miles per second had struck the animals. These were impactites, molten rock particles flung at incredible speeds during an asteroid explosion. Their presence suggested a violent event, one that likely killed both animals and humans. Suddenly, the Karanka's impact, the meteor crater, and the Alaskan tusks formed a timeline. Small to medium asteroids had struck Earth repeatedly throughout its recent history. Many events were local, devastating but not globally transformative. Yet they carried a consistent message. Impacts do not need to be world-ending to change history. The media began picking up on the pattern. Headlines asked, "Are we safe from the next one?" Television specials juxtaposed footage of Tunguska forests with aerial views of modern cities. Social media buzzed with amateur skywatchers posting meteor sightings, each claiming to have caught the next Karankas. But beneath the noise, serious scientific conversations were taking shape. Astrophysicists recalculated atmospheric entry models, questioning assumptions about the threshold at which objects burn up. Geologists began reassessing unexplained blackened layers in ancient soils. Archaeologists looked at abrupt cultural disappearances through a new lens. Governments, however, remained largely silent. Publicly, agencies emphasized that large asteroid impacts were rare and well-monitored. But internally, defense and space organizations knew that their systems were nearly blind to objects under a few dozen meters across. There was no reliable way to detect or intercept something like the Karanka's meteor before it struck. And so, scientists turned their gaze deeper into history. If modern instruments had missed these smaller objects, perhaps the answers lay buried in ancient layers of Earth. Layers that might record the aftermath of impacts too subtle to leave massive craters, but too powerful to ignore. Part 3: The Black Mat Mystery. In a quiet cave in northern Ohio, 30 feet beneath the surface, archaeologist Ken Tankersley carefully brushes away layers of ancient soil. The air is still, the light dim. For years, Tankersley had been excavating this site, looking for traces of the Clovis culture, one of the earliest known societies in North America. But on this day, his team uncovered something that would shift the conversation about asteroid impacts from the realm of astronomy to archaeology. Lying between layers of soil was a thin, carbon-rich band unlike anything above or below it. To archaeologists, this was known as the black mat. It was dark, glassy in places, and smelled faintly of burnt material even after thousands of years underground. Radiocarbon dating placed this layer at approximately 13,000 years ago, the same time the Clovis culture abruptly vanished from the archaeological record. Beneath the black mat, evidence of megafauna abounded. Mammoth bones, giant sloth remains, tools, and signs of human activity. Above it, nothing. It was as if life had been suddenly and violently interrupted. Tankersley was not the first to find such a layer. Similar black mats had been discovered at sites across North America, but most researchers attributed them to natural fires or gradual climate shifts. What set this discovery apart was the meticulous preservation of the layer and the abruptness of the cultural disappearance surrounding it. The Clovis people, known for their distinctive stone tools, had flourished for centuries. Then, without warning, their presence vanished, along with many of the large mammals they hunted. Initial analysis revealed that the black mat was composed of charcoal, soot, and burned organic material, but not in patterns consistent with typical forest fires. Instead, the burning appeared sudden and intense. Bones found within the layer were scorched at temperatures far exceeding what open-air human fires could achieve. To cremate a human body naturally, Tankersley explained, you need to burn it for days. This was something else. This was instantaneous. The absence of a crater puzzled scientists. If an asteroid had caused this event, where was the impact site? Unlike Arizona's meteor crater, no obvious depression marked the landscape. This led to a provocative hypothesis. Could an asteroid have been large enough to destroy an entire culture, yet so small, or so uniquely situated, that it left no trace? To explore this, Tankersley sent samples of the black mat to laboratories equipped with electron microscopes. Under magnification, researchers observed something remarkable. Tiny, nanometer-sized diamonds embedded in the layer. These detonation diamonds form only under extreme pressure and heat, conditions typical of a high-velocity extraterrestrial impact. They were identical to diamonds found at known impact sites, but their widespread distribution across multiple North American locations suggested a massive aerial explosion, not a single point of impact. The idea echoed the Tunguska event of 1908, when a small asteroid exploded mid-air over Siberia, flattening 800 square miles of forest without leaving a crater. But the Ohio evidence pointed to something even more extensive, an explosion large enough to devastate entire ecosystems and cultures. The scientific community was split. Some archaeologists argued that the black mat was evidence of massive wildfires triggered by climate change at the end of the last ice age. Others pointed to the presence of extraterrestrial materials, impact spherules, magnetic rains, and detonation diamonds, as clear signs of a cosmic event. The debate spilled into conferences, academic journals, and late-night television. It wasn't just about history. It was about how vulnerable humanity might still be to similar, invisible impacts. Meanwhile, atmospheric scientists began revisiting models of how asteroids interact with ice. Around 13,000 years ago, much of North America was blanketed by the Laurentide ice sheet, up to a mile thick in some areas. Professor Peter Schultz of Brown University proposed that an asteroid could have slammed into this ice, exploded with immense energy, and then left no crater because the impact site was effectively erased when the ice melted. It's like a perfect cosmic crime, he remarked. The evidence hides itself. To test this theory, Schultz used NASA's vertical gun range outside San Francisco to simulate impacts. He fired tiny glass beads at mile-thick slabs of ice under atmospheric conditions similar to Earth's. When the beads struck, they produced massive explosions, but left only shallow depressions. Once the ice melted, the surface appeared untouched. No crater. No obvious scar. Yet the explosive force would have been devastating, capable of obliterating entire regions. If such an impact had occurred over the Laurentide ice sheet, the energy released could have incinerated forests, destabilized climates, and annihilated species and cultures across a continent. The black mat wasn't just a layer of soot. It was a silent witness to an event so intense that it changed the trajectory of life in North America. For scientists piecing this puzzle together, the realization was unsettling. The Clovis disappearance, the mammoth tusks, the black mat, and modern events like Karanka's were not isolated mysteries. They were chapters in a repeating pattern of small to medium asteroid strikes, often aerial explosions, that leave few scars but lasting consequences. And if such an event happened 13,000 years ago with no warning, what would happen if something similar appeared in our skies tomorrow? Part 4: The Unseen Threat. By the time the black mat findings made their way into academic journals, the conversation around asteroid impacts had shifted dramatically. No longer were these events viewed solely as ancient catastrophes or distant possibilities. They were recognized as a continuum, a series of recurring incidents that ranged from the barely detectable to the civilization ending. But perhaps the most alarming realization was that many of these impacts would not be spotted in time. In fact, most would not be spotted at all. In 1998, in response to growing concern from the scientific community, the U.S. Congress instructed NASA to launch the SpaceGuard survey, an ambitious program aimed at identifying and tracking near-Earth asteroids large enough to cause massive destruction. The initial goal was straightforward: find 90% of asteroids at least 1 kilometer in diameter. If one of these giants were on a collision course with Earth, it would be spotted years, perhaps decades, in advance, allowing humanity time to prepare a defense. But as the program advanced, an unsettling gap became clear. While telescopes were well equipped to detect kilometer-scale asteroids, smaller but still dangerous objects, hundreds of feet across, were slipping by unnoticed. These were the Tunguskas, the meteor craters, the cases, the rocks that wouldn't end civilization, but could destroy cities, destabilize economies, or wipe out entire regions in seconds. At the University of Arizona's Catalina Sky Survey, asteroid hunter Ed Bescher and his team spent night after night imaging patches of the sky. Their telescopes took 4 exposures of the same star field over 40 minutes. In these images, stars appeared fixed, but asteroids, closer and moving, would drift slightly between frames. By blinking the images rapidly, astronomers could detect these moving specks of rock hurtling through space. The technique was effective for large objects. But the smaller the asteroid, the fainter the signal. Many slipped through undetected, hidden in the noise of the universe. Then, in 2004, astronomers got a wake-up call. At the Kitt Peak Observatory in Arizona, they detected a new object moving through the night sky. Closer inspection revealed it to be an asteroid roughly 900 feet wide, 10 times the size of the object that created Meteor Crater. They named it Apophis, after the Egyptian god of chaos. Early trajectory calculations were alarming. Apophis appeared to be on a potential collision course with Earth, with a disturbingly high probability of impact in the year 2029. If Apophis were to strike, the consequences would be catastrophic. Regional devastation on the scale of a small country. Shockwaves, tsunamis, mass infrastructure collapse. Dr. Richard Binzel at MIT calculated that an Apophis impact would unleash energy equivalent to 375 megatons, more than 20,000 times the bomb dropped on Hiroshima. Entire metropolitan regions could be annihilated in an instant. As new observations refined the asteroid's path, the likelihood of a direct impact decreased. But the close pass remained shocking. Apophis would pass just 18,000 miles from Earth, closer than many geostationary satellites. For a brief window in 2004, humanity had stared down a potential civilization-scale impact and realized how unprepared it was. Meanwhile, scientists began to confront another sobering fact. Many smaller objects simply don't reflect enough light to be spotted in time. A 100-foot-wide asteroid like the one that flattened Tunguska might only be detected days, or even hours, before impact. If it approached from the direction of the sun, it could be effectively invisible until it entered the atmosphere. Government agencies convened quiet meetings. Behind closed doors, defense and space officials debated strategies. Publicly, they reassured citizens that the largest objects were well monitored. Privately, they acknowledged that the most likely cause of the next catastrophic impact was not a giant rock from deep space, but a smaller, faster, and far less detectable object. This vulnerability was underscored in 2013, when a 65-foot asteroid exploded in the sky above Chelyabinsk, Russia. The blast was equivalent to a 500-kiloton explosion, 30 times the energy of Hiroshima. Over 1,500 people were injured, mostly by shattered glass as shockwaves tore through buildings. The asteroid had not been seen beforehand. It arrived without warning, streaking out of the bright morning sun. The message was unmistakable. Earth's greatest existential threats may arrive silently, hiding in plain sight. Telescopes and surveys, as advanced as they are, remain blind to vast swaths of the sky when it comes to small and mid-sized asteroids. And these are precisely the objects that have struck most often throughout history. For the scientific community, this realization marked a turning point. It was no longer enough to search for cosmic giants. Attention had to shift toward the swarm, the countless smaller objects moving through near-Earth space like shrapnel in a vast, invisible minefield. They may be harder to see, but history, from Clovis to Karankis to Chelyabinsk, shows that they strike with devastating regularity. As governments began to fund new detection systems and theoretical deflection technologies, one thing became clear: understanding the science of these impacts would be crucial. And that meant returning to the core of the problem, the physics of asteroid impacts, the data behind their trajectories, and the models that might give us precious hours or minutes of warning. Part 5: The Physics of a Collision. When an asteroid enters Earth's atmosphere, it does not simply fall. It arrives like a bullet, except far faster and far more destructive. Understanding what happens in those final seconds is at the heart of modern impact science. It's also the key to predicting which objects will burn harmlessly in the sky and which will become history-altering events. Asteroids typically travel through space at speeds ranging from 25,000 to 50,000 miles per hour. As they encounter the upper atmosphere, friction compresses the air in front of them, generating intense heat and pressure. Small objects disintegrate completely, scattering harmlessly as glowing meteors. Larger bodies, however, build up immense kinetic energy, and that energy has to go somewhere. When a speeding car crashes into a brick wall, the metal crumples and the kinetic energy is converted into sound, heat, and destruction. An asteroid behaves the same way, but on a scale beyond human experience. The impact energy depends on two factors: mass and velocity. Even a small increase in velocity dramatically amplifies the force. At 50,000 miles per hour, a 150-foot wide rock carries the energy of multiple nuclear bombs. Upon impact, this energy is released almost instantaneously, generating temperatures that can exceed those on the surface of the sun. The ground liquefies. Air is pushed aside in a rapidly expanding shockwave. For mid-sized asteroids, this typically occurs not on the surface but in the air itself, creating what scientists call an airburst. The Tunguska event of 1908 remains the most famous example of an airburst. A 100 to 200-foot asteroid exploded roughly 5 miles above Siberia, flattening 800 square miles of forest. For decades, scientists assumed the object had to be massive to cause such destruction. But recent supercomputer simulations by Dr. Mark Boslow in 2007 revealed something surprising. The asteroid may have been as small as 100 feet across. Previous models had treated the explosion like a stationary nuclear detonation. Boslow's updated models accounted for the asteroid's speed and trajectory. When it exploded, the energy didn't radiate evenly in all directions. It continued downward, focused like a cosmic blowtorch. A smaller object, moving fast, could wreak far more havoc than anyone had previously believed. This realization fundamentally altered how scientists assess impact risks. Tunguska-sized asteroids, once thought to strike only every few thousand years, may actually hit Earth every few hundred years. And because they are much smaller and dimmer than kilometer-scale objects, almost none of them are detected in advance. Laboratories around the world have been experimenting with high-speed impact simulations to understand these dynamics. At NASA's Ames Research Center, scientists use the vertical gun range to fire projectiles at extreme velocities into various materials, sand, rock, ice, to simulate atmospheric entry and surface impact. These experiments reveal how different compositions behave on entry. A solid metallic asteroid penetrates deeper. A rubble pile asteroid, essentially a loose collection of rocks held together by weak gravity, breaks apart higher in the atmosphere, but can still produce devastating airbursts. Meanwhile, geologists study impactites, melted rock fragments formed during impacts, to reconstruct ancient events. These particles, sometimes only millimeters across, can be scattered dozens of miles from the impact site at speeds 2 to 3 times faster than rifle bullets. In Arizona, impactites found miles from meteor crater tell the story of the asteroid's entry angle and explosion dynamics. In Alaska, the same kinds of particles embedded in mammoth tusks offer a record of a mid-air blast that likely occurred 34,000 years ago. Statistical modeling paints a sobering picture. According to current estimates, Earth is struck by Tunguska scale objects 100 to 200 feet, roughly every 300 to 500 years. City-destroying objects 300 to 600 feet, every several thousand years. Civilization-scale objects 1 kilometer and above, only every few 100,000 years. This means that while planet killers are rare and well-tracked, smaller objects strike far more often, and the vast majority go unnoticed until impact or airburst. The Chelyabinsk event in 2013, where a 65-foot asteroid exploded over Russia injuring over 1,500 people, is statistically ordinary. What made it extraordinary was that it occurred over a populated region in the age of smartphones, allowing humanity to witness, film, and measure an event that has likely happened countless times throughout history in remote areas. Understanding the composition of asteroids is another critical piece of the puzzle. Observations with spectrometers, like those used at the Mauna Kea Observatory in Hawaii, allow scientists to analyze the light reflected off asteroids and infer their mineral makeup. Some are composed mostly of rock. Others contain metals like nickel and iron. A few are rich in carbonaceous material, similar to ancient meteorites found on Earth. These differences determine how an asteroid will behave on entry, whether it will explode mid-air, strike the ground, or fragment into multiple pieces. This last scenario, fragmentation, is particularly dangerous. If a nuclear device or natural stress causes a large asteroid to break into several smaller bodies, each fragment can follow its own trajectory, striking multiple locations like a cosmic shotgun blast. Instead of one crater, there could be dozens. And unlike a single predictable impact, a fragmented strike is far harder to model or intercept. As the science deepens, so does the urgency. With better models, scientists can predict impact effects more accurately. But prediction is useless without detection. And detection, as astronomers increasingly admit, is still our weakest link. The physics of collision is well understood. The statistics are sobering. The question now is whether humanity can apply this knowledge in time to make a difference. Part 6: Eyes on the Sky. At first glance, the night sky seems calm, unchanging. But through the lens of modern telescopes, it is anything but. Thousands of small objects move silently through the darkness, weaving invisible paths that occasionally cross Earth's orbit. Detecting these objects early is humanity's best hope for survival. And yet, the challenge is far greater than most imagine. Around the world, a network of observatories works every night to scan the heavens for near-Earth objects, NEOs. The backbone of this effort lies in surveys like the Catalina Sky Survey in Arizona, Pan-STARRS in Hawaii, and the Linear Project in New Mexico. Each employs high-resolution telescopes to repeatedly photograph sections of the sky. Software then compares images, looking for tiny dots that shift between frames, signatures of asteroids. Despite their sophistication, these systems face fundamental limitations. Many NEOs are dark, reflecting little sunlight. Carbon-rich asteroids, in particular, are almost invisible until they are uncomfortably close. Others approach from angles that make them effectively hidden, such as the direction of the sun. Ground-based telescopes simply cannot look that way without being blinded. In 2013, this limitation became painfully clear. The Chelyabinsk asteroid came from a sunward trajectory. It went undetected, entered Earth's atmosphere, and exploded with the energy of 30 Hiroshima bombs, all without a single warning. Scientists admitted afterward that even if they had been looking directly at it, their instruments likely wouldn't have seen it in time. This vulnerability has led to the development of space-based detection systems, which can look outward from orbit, free from atmospheric distortion and the glare of the sun. NASA's NEOWISE mission, a repurposed space telescope, has already discovered hundreds of previously unknown NEOs by detecting their infrared signatures, the heat they emit. Unlike optical light, infrared can reveal dark asteroids that are otherwise invisible against the blackness of space. Building on NEOWISE's success, NASA plans to launch NEO Surveyor, a dedicated infrared space telescope designed to find 90% of hazardous NEOs larger than 460 feet. Operating from the gravitationally stable L1 point between Earth and the Sun, it will scan vast regions of space, including the sunward direction that ground telescopes cannot observe. If successful, it could provide years of warning for many dangerous objects. But the mission is still in development, and funding delays have already pushed its timeline further into the future. Meanwhile, European and Asian space agencies are developing their own complementary systems. The European Space Agency's Fly-Eye telescope in Italy uses a novel wide-field optical design that mimics the structure of an insect's eye, allowing it to capture massive portions of the sky simultaneously. In Japan, researchers at the Subaru telescope on Mauna Kea are testing new adaptive optics to detect faint, fast-moving objects with unprecedented precision. Private efforts are also emerging. Startups are experimenting with autonomous microsatellites, swarms of small, inexpensive sensors that could act as an early warning net encircling the planet. Despite these advances, the truth remains sobering. Current surveys are excellent at finding large asteroids years in advance. But for objects under 150 feet, those most likely to explode over cities or oceans, the detection window often shrinks to days or hours, if they are seen at all. Statistically, hundreds of thousands of these objects cross Earth's orbit, and only a tiny fraction have been catalogued. To illustrate this, NASA periodically conducts blind tests. Astronomers are given archival data with an undisclosed asteroid hidden within it. Their task: find it. Even experienced teams sometimes fail, especially if the asteroid is dim or its movement is subtle. These exercises underscore a hard reality. Detection is as much about algorithmic sophistication as it is about telescope power. Adding to the complexity is the sheer volume of data. Each night, Pan-STARRS alone produces tens of terabytes of images. Sifting through this flood of information requires advanced machine learning algorithms capable of distinguishing real moving objects from camera noise, cosmic rays, and software artifacts. In recent years, AI has become an increasingly valuable tool, catching objects that human observers might miss. But AI, too, has its limits. False positives remain common, and the most dangerous asteroids are often those that look like nothing at all, barely brighter than the background. Some researchers have begun exploring more unconventional detection methods. One idea involves using gravitational perturbations, tiny wobbles in the orbits of known satellites or space debris, to infer the presence of nearby asteroids. Another approach proposes global infrasound networks, originally designed to detect nuclear tests, to listen for the low-frequency booms of impacts and near misses, providing a kind of backward detection after the fact. These methods are promising, but they remain experimental. What becomes clear in all these efforts is that detection is a race against time. Every day, undetected asteroids zip past Earth, often within lunar distance. Some are discovered only after they've already flown by, a cosmic near-miss logged quietly in astronomical databases. Each of those events could have been a headline-making disaster if the object's trajectory had shifted by just a fraction of a degree. The sky is not empty. It is alive with motion, filled with countless wanderers, some harmless, others potentially catastrophic. And despite our telescopes, satellites, and algorithms, many of them remain unseen until the last possible moment. Part 7: Models, Uncertainties, and Cosmic Coincidences. The more scientists observe the sky, the clearer one unsettling fact becomes: prediction is not certainty. Even with the most advanced telescopes, precise orbital models, and powerful computers, forecasting the path of a small asteroid is riddled with uncertainties. The universe is a dynamic, chaotic system, and a single pebble-sized fragment can alter the trajectory of a rock the size of a building. When astronomers detect a new object, they typically observe it for only a short period, sometimes just hours. From this limited data, They calculate a preliminary orbit using Newtonian mechanics and celestial dynamics. But in these early stages, the error margins are enormous. A slight measurement error in speed or angle can lead to predictions that diverge wildly over time. Within weeks, an asteroid that initially looked harmless can suddenly appear to have a small but non-zero chance of hitting Earth. Conversely, a seemingly dangerous object can vanish into the background once better data refines its orbit. This was precisely the case with Apophis in 2004. For a brief, tense period, calculations suggested a collision with Earth in 2029 was alarmingly possible. As more observations came in, astronomers refined the orbit and found that it would pass close, but safely. Yet even then, uncertainty lingered. If Apophis were to pass through a specific gravitational keyhole, a region of space less than a kilometer-wide Earth's gravity could tweak its trajectory just enough to set up a collision on a later pass in 2036. The odds were small, but the implications were enormous. Detecting and modeling such keyholes requires extraordinary precision, and the margin for error can be measured in mere meters. The uncertainties grow further with small asteroids, which are more vulnerable to subtle forces like the Yarkovsky effect. This phenomenon occurs when sunlight heats one side of a rotating asteroid, and the re-radiated heat acts like a tiny thruster, gradually altering its orbit over years or decades. For a mile-wide asteroid, the effect is negligible. For a rock the size of a house, it can make the difference between a harmless pass and a direct hit. Accounting for the Yarkovsky effect requires not only accurate measurements of the asteroid's size and shape, but also its rotation rate, thermal properties, and surface composition, details that are often unknown. International space agencies collaborate through groups like the International Asteroid Warning Network, IAWN, and the Space Mission Planning Advisory Group, SMPAG, to pool data, refine models, and coordinate responses. NASA's Center for Near-Earth Object Studies, CNEOS, maintains a running list of every known object with even a remote chance of impacting Earth, updating trajectories as new data arrives. The European Space Agency operates its NEO Coordination Center in Italy, performing parallel calculations and issuing independent assessments. Despite this global coordination, the modeling process is a race against time. Many asteroids are visible for only a brief window before they disappear into the darkness again. If follow-up observations aren't secured quickly, their orbits become increasingly uncertain, and the object may effectively go missing. Hundreds of such objects are currently listed as lost, initially detected but never tracked long enough to pin down their future paths. Some of these could be harmless. Others could reappear decades from now on a dangerous trajectory. To manage this uncertainty, agencies classify asteroids using the Torino Impact Hazard Scale, a 0 to 10 system that estimates the likelihood and potential consequences of an impact. A rating of 0 means no risk. A 10 represents a certain global catastrophe. Most newly discovered asteroids start at 0, occasionally rising to 1 or 2 as more data comes in. Very few have ever reached level 4 or higher, and those that did were later downgraded after additional measurements. But the scale is as much a communication tool as a scientific one. It's designed to convey urgency without sparking unnecessary panic, a delicate balance when the difference between close miss and direct hit can hinge on data measured in fractions of a degree. The human element adds another layer of complexity. In 2019, for example, the European Space Agency announced that asteroid 2006 QV89 had a 1 in 7,000 chance of impacting Earth that September. Media outlets seized on the story, and headlines about a potential doomsday rock went viral. Scientists scrambled to explain that the risk was extremely low. Weeks later, refined observations ruled out any chance of impact. But the episode revealed a troubling reality. The gap between scientific caution and public perception can quickly amplify fear, misinformation, and even political pressure. Some researchers have begun exploring probabilistic modeling, treating asteroid predictions less like fixed orbits and more like weather forecasts. Instead of definitive statements, it will hit or it won't, they generate impact probability maps, showing regions where a potential strike might occur based on current uncertainties. These models evolve as new data arrives, shrinking or expanding the corridor of risk. It's a dynamic, adaptive approach that acknowledges the chaotic nature of orbital mechanics. And then there are the cosmic coincidences, the moments that remind scientists how thin the line can be between normalcy and disaster. On February 15, 2013, as the Chelyabinsk asteroid exploded over Russia, another much larger object, asteroid 2012 DA14, 150 feet across, passed just 17,000 miles from Earth. The two events were unrelated, but the timing was uncanny. One object missed Earth by a cosmic hair. The other struck without warning. Together, they provided a glimpse of how unpredictable the near-Earth environment truly is. In the end, modeling the behavior of asteroids is not about certainty, it's about narrowing the unknowns. Every observation, every refined calculation is a step toward clarity. But even with the best data and algorithms, the universe remains a place where small forces over long timescales can produce enormous consequences. And that makes the work not just scientific but existential. Part 8. Natural patterns or something else? For most of human history, impacts were regarded as acts of nature, random, unpredictable, unstoppable. But as data accumulated, a deeper question emerged. Are all impact events purely natural, or could some phenomena reflect something more complex? Either hidden natural patterns we have yet to fully understand, or, more provocatively, something non-natural. The first layer of this question is straightforward: natural clustering. Statistical studies by NASA's Jet Propulsion Laboratory, JPL, and the European Space Agency have shown that impact events are not perfectly evenly distributed over time. Instead, they appear in clusters, periods of heightened activity separated by centuries or millennia of relative calm. Some of these clusters align with known astronomical cycles, such as when Earth passes through dense debris streams left behind by disintegrating comets. Meteor showers like the Perseids are harmless examples of this. But occasionally, the streams contain objects far larger than dust. Computer simulations suggest that as comets break apart, they can leave behind coherent streams of large fragments. Rocks tens to hundreds of feet wide, traveling along similar orbits. When Earth's path intersects such a stream, impacts can occur in a rapid series, sometimes over just decades. This model could explain why the black mat layer appears across multiple sites in North America around the same time 13,000 years ago. Instead of a single impact, Earth may have passed through a dense swarm of cometary debris, producing multiple Tunguska-scale airbursts over the ice sheets. Similar patterns appear in the geological record. Stratigraphic layers in Greenland ice cores show spikes in platinum group elements, rare metals associated with extraterrestrial material, at intervals that suggest more than isolated random strikes. These intervals sometimes correlate with abrupt climate events, such as the Younger Dryas, a sudden and intense cooling period that began about 12,800 years ago. While volcanic activity and ocean circulation shifts have been proposed as explanations, the widespread presence of high-temperature impact markers like nanodiamonds and magnetic spherules strongly points to a cosmic trigger. Still, nature has a way of hiding its mechanisms. Some impacts may be tied to resonance cycles involving the gravitational influence of Jupiter and Saturn. These giant planets subtly nudge asteroid belts, occasionally sending fragments inward toward Earth on long timescales. Others might be linked to periodic disturbances in the Oort cloud, a vast shell of icy bodies at the edge of the solar system, caused by the solar system's oscillations through the galactic plane. Every 30 to 35 million years, these oscillations may increase the number of long-period comets entering the inner solar system. While this operates on timescales far longer than human history, the idea underscores that impacts are not truly random. They follow natural rhythms, some subtle, some grand. But then there are the anomalies, observations that don't fit neatly into known natural models. A handful of impacts exhibit unusual entry angles, velocities, or fragmentation patterns that are difficult to reconcile with standard trajectories. For example, the 1908 Tunguska event had an unusually shallow entry angle and fragmented higher in the atmosphere than most objects of similar size. Some early Soviet scientists speculated wildly, proposing everything from antimatter to alien spacecraft. Modern analyses attribute these anomalies to the object's composition, likely a fragile stony or icy body, but the fact remains. Not all impact events behave as expected. Similarly, the Karankas meteorite in 2007 defied atmospheric models by remaining intact despite its small size, producing a ground impact that, by all predictions, should not have occurred. Subsequent studies revealed that its unusual strength, a dense chondritic composition, and steep trajectory allowed it to punch through the atmosphere like a cosmic dart. Events like these remind scientists that our models, while powerful, are still approximations. Nature often finds ways to surprise. A more speculative but persistent question involves technosignatures, hypothetical evidence of non-human intelligence. A few fringe researchers have asked whether some anomalous impact phenomena could, in principle, mask artificial activity. Could highly advanced civilizations use controlled asteroid trajectories for signaling, or as relic engineering structures that now drift unnoticed among natural debris? Mainstream science treats these ideas cautiously, emphasizing that extraordinary claims require extraordinary evidence. So far, no impact event has provided verifiable data suggesting artificial origin. Every anomaly has, eventually, found a natural explanation, though sometimes after decades of investigation. What makes this question scientifically interesting is not the alien hypothesis itself, but the methodology it inspires. By scrutinizing impact events for deviations from natural models, scientists refine their understanding of what natural actually looks like. This, in turn, sharpens their ability to detect anything that might truly be unusual. NASA's SETI, Search for Extraterrestrial Intelligence, programs, for instance, have considered monitoring asteroid trajectories for signs of deliberate alteration, such as synchronized movements or propulsion-like accelerations. So far, nothing of that kind has been observed. Ultimately, the line between natural and non-natural is not defined by sensational claims, but by data. Impact phenomena, once dismissed as mere accidents of nature, now reveal intricate cosmic patterns, streams, cycles, resonances, that shape Earth's history in ways humanity is only beginning to grasp. Whether through cometary debris swarms, gravitational keyholes, or the slow dance of celestial bodies over millions of years, the sky is neither random nor malevolent. It follows rules, some we understand, others still hidden. And as scientists peel back these layers, one truth becomes clear. Knowing the patterns means knowing the risks. If we can decipher the rhythms of cosmic bombardment, we might one day predict, not just react to, the next great impact. Part 9: Patterns Across Time and Civilizations. When archaeologists in North America first uncovered the black mat layer, few imagined that similar stories might be buried beneath soils and ruins across the globe. But as evidence accumulated, historians, climatologists, and astrophysicists began to notice striking parallels between impact events and pivotal moments in human history. These weren't just geological curiosities, they were turning points that shaped civilizations. Take, for example, the abrupt collapse of the Akkadian Empire around 4,200 years ago. Centered in Mesopotamia, the Akkadians built one of the earliest great empires, uniting vast territories under a single rule. Their sudden decline has long puzzled historians. Recent high-resolution climate records from lakebeds and cave deposits in the Middle East reveal a rapid and severe cooling event around that time, likely triggered by massive atmospheric disturbances. While volcanic activity remains a candidate, some researchers have pointed to extraterrestrial dust signatures, platinum anomalies, and microspherules in sediment layers, as potential evidence of a cosmic airburst or impact somewhere in the northern hemisphere. Such an event could have injected fine dust into the atmosphere, blocking sunlight, cooling the climate, and devastating agricultural systems upon which the empire depended. Further east, in what is now modern-day Syria, the city of Tal el-Hammam was suddenly obliterated around 1650 BCE. Archaeological excavations reveal melted pottery, shocked quartz, and a destruction layer several feet thick, signatures typically associated with high-temperature blasts, not conventional warfare. The heat was so intense that mud-brick walls turned to glass. Some researchers have compared the evidence to Tunguska-like airbursts, proposing that a mid-air explosion leveled the city in an instant. Ancient oral traditions from the region, including stories preserved in religious texts, speak of a blinding light and fire from the sky, echoing what modern witnesses described in Chelyabinsk centuries later. In North America, long after the Clovis culture vanished, Maya inscriptions mention celestial omens preceding periods of drought and collapse. While these texts are poetic and symbolic, recent ice core data from Greenland and Antarctic archives show abrupt spikes in atmospheric dust and platinum group elements at roughly the same times. Some climatologists suggest that even modest airbursts, hundreds of miles away, can trigger regional climate anomalies by lofting fine debris into the stratosphere, subtly altering rainfall patterns for years. In pre-industrial societies highly dependent on agriculture, such disturbances could spell disaster. The Younger Dryas cooling event, which began 12,800 years ago, remains the most dramatic example. Ice core records show an almost instantaneous drop in global temperatures, by as much as 8 degrees Celsius in some regions, lasting over 1,000 years. For decades, scientists attributed this to changes in ocean circulation. But the widespread presence of nanodiamonds, magnetic spherules, and carbon-rich layers across multiple continents suggests a cosmic trigger. Earth passing through a dense debris field, possibly from a disintegrating comet. Whether a single impact or a series of airbursts, the effect was global, reshaping ecosystems, forcing human migrations, and likely accelerating the extinction of large Ice Age mammals. These connections between celestial events and historical turning points have profound implications. They suggest that impacts are not just random background noise, but periodic agents of change, sometimes destructive, sometimes transformative. A single well-placed airburst can alter climate systems, shift political structures, or even reshape cultural narratives. For ancient societies, which lacked the scientific framework to understand these phenomena, such events were often interpreted as acts of gods. Fire from the heavens, divine punishment, or cosmic omens. Temples were built, rituals performed, calendars aligned with the skies, not merely out of reverence, but perhaps also as attempts to predict or appease forces they could not control. In modern times, the framing has shifted from mythology to geopolitics. A Chelyabinsk-sized airburst over a populated region today could be mistaken for a nuclear detonation, triggering international crises. In fact, during the Cold War, both the United States and the Soviet Union monitored infrasound networks designed to detect atmospheric explosions. Some of the signals recorded were not bombs, but meteors exploding high above the atmosphere. These detections were often classified to avoid revealing sensor capabilities. Ironically, the first global asteroid impact detection network was built for nuclear treaty verification. As detection systems improved, governments began to realize that asteroid impacts have political consequences, not just physical ones. Who is responsible for issuing warnings? How should nations respond if a city-threatening asteroid is discovered weeks before impact? If one country launches a deflection mission, does that create international legal liability if the object's trajectory is altered toward another region? These questions remain largely unanswered. At the same time, the cultural memory of impacts persists in myths, religious texts, and oral traditions around the world. From Aboriginal Australian fire devil stories that match crater dates to Native American legends describing the day the sky fell, ancient people recorded these cosmic encounters in their own language. For modern scientists, these stories are more than folklore. They can point to real events, waiting to be corroborated by geological evidence. By viewing impacts not only through telescopes and models but also through historical and cultural lenses, a new picture emerges. One where the sky has repeatedly intersected with human destiny. Sometimes as destroyer, sometimes as catalyst, always as a force beyond human control. And as our detection capabilities improve, we are beginning to realize something that ancient civilizations could only sense through myth: The rhythms of the cosmos shape the rhythms of history. Part 10: A global wake-up call. By the early 21st century, a quiet but profound shift began to occur in how the world viewed asteroid impacts. What had long been the domain of astronomers and geologists was now entering the arenas of international security, policy, and global cooperation. Events like Chelyabinsk served as stark reminders that the sky can deliver geopolitical shocks, even without a single weapon being fired. On February 15, 2013, as the sun rose over the Ural Mountains, a 65-foot asteroid entered Earth's atmosphere at nearly 40,000 miles per hour. The resulting airburst released energy equivalent to half a megaton of TNT. Windows shattered across 6 cities, over 1,500 people were injured, and countless dashcams captured the brilliant flash and shockwave. Within minutes, videos flooded the internet. News outlets across the globe replayed the footage in a loop. For the first time in human history, a significant cosmic impact unfolded live on millions of screens. What startled policymakers wasn't just the explosion, it was the fact that no one saw it coming. Telescopes had missed it. Warning systems were silent. Had the object entered at a slightly different angle, it could have exploded directly above a major city center, causing thousands of deaths and billions in damage. The realization that a natural object could mimic the effects of a small nuclear detonation sent shockwaves through defense establishments. In Washington, Moscow, Brussels, and Beijing, high-level briefings followed. Military officials analyzed the event as if it were an attack. Could a future airburst trigger false alarms on early warning systems? Could nations misinterpret the flash and launch retaliatory strikes before realizing it was natural? These weren't idle fears. During the Cold War, U.S. early warning satellites had occasionally detected unexpected atmospheric flashes later traced to meteor entries. The risk of miscalculation remains very real. In response, organizations that had previously operated in separate spheres began to coordinate more closely. NASA's Planetary Defense Coordination Office, PDCO, established in 2016, became the central hub for detecting and characterizing hazardous objects. It works with the U.S. military, European agencies, and international observatories to ensure that potential impact threats are communicated rapidly and accurately. On the diplomatic front, the United Nations took a rare proactive step. In 2013, the UN General Assembly formally endorsed the creation of the International Asteroid Warning Network, IAWN, and the Space Mission Planning Advisory Group, SMPAG. Their mandates are clear: share data, develop standardized communication protocols, and plan coordinated responses. For the first time, asteroid defense became a matter of international policy, not just scientific interest. These developments were not purely theoretical. In June 2019, NASA hosted a planetary defense exercise simulating the discovery of a fictional asteroid on a collision course with Earth. Over several days, scientists, engineers, diplomats, and emergency managers role-played how they would respond. The scenario ended with the fictional asteroid impacting Central Europe after deflection missions failed. The exercise revealed gaps: disagreements over who had authority to act, how to share classified tracking data, and how to manage public communication without inciting panic. Meanwhile, real asteroids kept passing by. In 2020 QG, a refrigerator-sized rock, zipped past Earth just 1,800 miles above the surface, closer than many satellites, and was detected only after it had already passed. In 2021, a 100-foot asteroid, 2021 UA1, approached from the direction of the Sun and was detected just 4 hours before closest approach. Both events were harmless, but they highlighted the fragility of the current detection network. Adding to the urgency, humanity is entering an era of unprecedented space activity. Mega-constellations of satellites, planned lunar bases, and private space ventures mean that the consequences of an impact are no longer confined to Earth's surface. A small asteroid striking a satellite cluster in orbit could trigger cascading debris collisions, known as the Kessler syndrome, potentially crippling global communications and navigation systems. Internationally, there is growing recognition that no single nation can handle an impact threat alone. Unlike hurricanes or earthquakes, an asteroid impact is not bound by borders. An object discovered by a telescope in Chile may be headed toward Asia. A deflection mission launched by one nation could inadvertently shift the impact zone toward another. Legal frameworks for such scenarios are still primitive. Who gives the green light for a kinetic deflection? Who is liable if it fails? Parallel to policy efforts, public awareness has grown rapidly. Hollywood films like Armageddon and Don't Look Up dramatize the issue, often inaccurately, but they succeeded in embedding the concept of planetary defense into popular culture. Grassroots groups and amateur astronomers contribute valuable observations through global networks. In some countries, asteroid education is entering school curricula, not as science fiction, but as practical awareness of a real, measurable risk. But perhaps the most profound shift is psychological. For centuries, humanity viewed the cosmos as distant, immutable, and detached from daily affairs. Now, we are beginning to understand that cosmic events are part of our geopolitical and environmental reality. The sky is not passive background, it is an active participant in history. As detection systems expand, international cooperation strengthens, and planetary defense technologies evolve, the question is no longer if the world will face another significant impact. It is when and whether we will be ready when that moment comes. Part 11: Cosmic Rhythms and Long Shadows. Beneath the immediacy of near-Earth asteroid alerts and planetary defense drills lies something deeper, a set of cosmic rhythms that have shaped Earth's environment, climate, and even the trajectory of civilizations across tens of thousands, and in some cases, millions of years. Modern science is only beginning to map these patterns. What emerges is a sobering picture. Earth's relationship with the cosmos is neither static nor random. It is cyclical, layered, and capable of casting long shadows over human history. One of the most significant influences comes from Earth's periodic encounters with cometary debris streams. These streams form when large comets disintegrate over time, shedding vast amounts of material into the inner solar system. While most of this debris produces harmless meteor showers, larger fragments, tens to hundreds of feet wide, can linger in coherent clusters, slowly drifting along the parent comet's orbit. When Earth's path intersects these clusters, impacts can occur in bursts, separated by decades or centuries. The Taurid complex, associated with Comet Encke, is a prime example. It spans hundreds of millions of miles and contains not just dust but massive, uncharted fragments. Astronomers have long suspected that Tunguska may have been caused by a member of the Taurid swarm. Recent radar observations and orbital simulations by Finnish astronomer Esko Laitinen suggest that Earth periodically passes through denser filaments of this swarm, dramatically increasing the probability of impacts for brief windows of time. Some researchers refer to these intervals as Taurid resonance swarms, occurring roughly every 2,000 to 3,000 years. During these periods, Earth essentially flies through a celestial minefield, with dozens of Tunguska-sized objects sharing similar orbits. Beyond cometary debris, the solar system itself is in motion, oscillating through the Milky Way's galactic plane every 30 to 35 million years. Some scientists propose that these oscillations periodically disturb the distant Oort cloud, sending a rain of long-period comets toward the inner solar system. Geological records show spikes in large impacts and mass extinctions that seem to correspond to these galactic cycles. While such timescales dwarf human history, they remind us that impacts are part of larger cosmic rhythms playing out far beyond our immediate neighborhood. Closer to home, subtle gravitational resonances with Jupiter and Saturn can destabilize asteroid orbits, nudging them toward Earth over thousands of years. These resonances act like invisible conveyor belts, slowly transferring rocks from the asteroid belt into Earth-crossing orbits. Once an object is caught in a resonance, its path can evolve chaotically, making long-term predictions extremely difficult. Some of today's near-Earth objects were likely placed on their current courses thousands of years ago by these quiet gravitational tugs. These cosmic patterns may have direct historical consequences. For example, some researchers have proposed that the onset of the Younger Dryas cooling event 12,800 years ago may correspond to Earth passing through a dense portion of the Taurid complex. Similarly, Minor climate disruptions and unexplained atmospheric dust spikes seen in ice cores have been tentatively linked to periodic Taurid encounters. If these encounters occur on predictable timescales, they could explain why impact events and climatic shifts appear in clusters, rather than as isolated random strikes. Understanding these rhythms is more than academic. If Earth is approaching another Taurid swarm encounter in the coming decades, a possibility currently under investigation, then the probability of mid-sized impacts could temporarily spike. Unlike a single large asteroid, which might be detected years in advance, a swarm consists of many smaller bodies, some invisible until the last moment. Traditional deflection strategies, which focus on tracking and altering the path of a single object, would be far less effective against a distributed threat. This realization is reshaping planetary defense strategy. Agencies like NASA and ESA are beginning to consider statistical defense models, focusing on probability zones rather than single-object trajectories. Instead of preparing for one catastrophic rock, they are exploring how to rapidly identify, prioritize, and respond to multiple simultaneous threats. It's a shift from a sniper mindset to one more akin to managing storms, anticipating the season, rather than predicting each raindrop. Culturally, these cycles have long been sensed, if not scientifically understood. Ancient calendars often track celestial events with remarkable precision. The Mayan long count calendar, for instance, is sometimes misrepresented as predicting apocalypses, but in reality, it reflects long astronomical cycles linked to planetary alignments and celestial phenomena. Aboriginal Australian oral traditions describe recurring fiery stars that appear every few generations. Even in medieval Europe, chronicles mention years of falling stars, periods of unusual meteor activity that coincided with famines and climatic anomalies. Modern science is now quantifying what ancient observers intuited, that the cosmos has its own seasons, some lasting decades, others spanning millennia. And humanity, whether aware of it or not, has always lived within these cycles. The implications are profound. If we can accurately map these cosmic rhythms, understand when Earth is likely to encounter dense debris streams, resonance zones, or galactic perturbations, we could move from reactive defense to predictive readiness. Instead of scrambling to respond to sudden impacts, we could treat them like hurricanes, inevitable, dangerous, but manageable with preparation. But the rhythms cut both ways. They remind us that the forces shaping our future have been in motion long before humanity existed, and will continue long after. Whether we choose to understand and adapt to these patterns or ignore them will determine whether the next cosmic encounter becomes a footnote in history or a defining moment. Part 12. The Unexpected Signal. In late August 2027, deep in the deserts of northern Chile, the Vera C. Rubin Observatory, the world's most advanced wide-field survey telescope, began its scheduled night scans as usual. Every few seconds, its massive 8.4-meter mirror swept across the heavens, capturing billions of stars and countless faint objects. For years, the Rubin Observatory had been a cornerstone of planetary defense, discovering more near-Earth objects than any other ground-based instrument. But on this night, something in the data caught the attention of astronomer Dr. Elena Martinez, a veteran sky surveyor with a reputation for spotting anomalies others overlooked. The object first appeared as a dim, fast-moving dot in one of the routine exposures. Its apparent magnitude was faint, barely distinguishable from background noise, but its movement across consecutive frames was unusually linear and precise, unlike the typical wobbling trails of natural small bodies tumbling through space. Martinez flagged the observation for automatic orbit calculation. Within minutes, the software produced a provisional trajectory. The numbers made her pause. The object, now temporarily designated 2027 QN1, was on an inbound trajectory that placed it well inside the lunar orbit within 10 days. Its estimated size, 120 to 150 feet. Big enough to cause a Tunguska-class explosion, small enough to evade early detection until now. What alarmed Martinez wasn't just the speed, but the entry angle, shallow, stable, and almost surgical. Natural asteroids often have chaotic rotations and small perturbations in their paths. QN1's orbit seemed too clean. Following standard protocol, Martinez submitted the data to the Minor Planet Center in Cambridge, Massachusetts. Within hours, telescopes in Hawaii, South Africa, and Australia pivoted to confirm the object. They all saw it. Its brightness curve indicated a highly reflective surface, possibly metallic. Infrared scans from the NEOWISE telescope revealed an unusual thermal profile, hotter than typical for its size and distance, as if it were absorbing and re-radiating energy more efficiently than a standard stony or carbonaceous asteroid. As the orbit was refined over the next 48 hours, something even more unsettling emerged. QN1's trajectory placed its closest approach at only 3,200 miles above the Earth's surface, closer than nearly all satellites. The probability of impact was initially estimated at 12%, but the uncertainty corridor, a narrow band of potential paths, ran directly across the Indian Ocean, through Southeast Asia, and into the Western Pacific. Major population centers like Jakarta, Manila, and Sydney lay within the corridor's fringes. The discovery triggered immediate alerts through the International Asteroid Warning Network, IAWN. Data packets were sent to NASA's Center for Near-Earth Object Studies, ESA's NEO Coordination Center, and defense agencies worldwide. In less than 24 hours, QN1 had moved from an obscure detection to the single most closely watched object in the solar system. And then came the leak. 3 days after the initial detection, a file labeled Rubin QN1 Full Data Internal appeared anonymously on a private astrophysics forum. The file contained raw observational data, orbit calculations, and, most controversially, a set of unverified radar returns from a classified U.S. tracking station on Kwajalein Atoll. These radar pings, if genuine, suggested that QN1 was spinning far more slowly than expected, almost stabilized. Such behavior was not impossible for a natural object, but extremely rare for something this small. Some radar specialists speculated that the object could be a fragment of an old metallic spacecraft, perhaps a defunct upper stage or long-forgotten satellite. But orbital backtracking showed no match with any known human-made debris. The leak exploded online. Amateur astronomers pored over the data, posting alternative orbit calculations. A faction of independent researchers claimed the trajectory matched the Taurid swarm's resonant filament, meaning QN1 might be part of a larger cluster following behind. If true, the world might not be dealing with one incoming body, but several arriving in a wave. Others, less cautious, seized on the slow rotation and metallic signature to fuel wild speculations about artificial origins. Governments scrambled to get ahead of the narrative. Official statements from NASA, ESA, and the UN stressed that QN1 was most likely a natural asteroid, possibly a rare metallic chondrite with a stable rotation. But behind closed doors, planetary defense agencies were racing to assess options. The object was too small and too close for a deflection mission, and its impact probability, while not guaranteed, was uncomfortably high. Emergency response simulations began quietly in several nations along the projected corridor. Contingency plans were drafted for possible evacuation zones, even as leaders struggled to keep the situation from causing public panic. As the days passed, new telescopic observations revealed something even stranger: a faint secondary object trailing QN1 by several thousand miles, following a nearly identical path. It was smaller, perhaps 30 feet wide, but it raised a chilling possibility. If Earth was indeed entering a dense filament of the Taurid swarm, QN1 might be only the first of several objects arriving in quick succession. The discovery, the leak, and the unexpected secondary detection sent shockwaves through the scientific and political communities. What had started as a routine night of observations in Chile was quickly escalating into the most serious near-Earth object threat of the century. One that combined scientific mystery, political pressure, and the very real possibility of an imminent impact. And in the background, telescopes continued to scan the skies, searching for others that might be lurking just behind. Part 13: Escalation. Within a week of QN1's discovery, the world had changed. What began as an obscure astronomical detection had morphed into a global emergency, unfolding with an intensity that no simulation had ever fully captured. Behind diplomatic smiles and carefully worded press releases, governments were entering a quiet state of crisis. At NASA's Jet Propulsion Laboratory in Pasadena, California, the Planetary Defense Coordination Office convened an emergency session. Representatives from ESA, JAXA, the Indian Space Research Organization, the Russian Roscosmos, and several classified military liaisons joined via encrypted links. The latest orbital refinement from Rubin Observatory and Pan-STARRS placed QN1's impact probability at 22%, a troubling increase, while the uncertainty corridor had narrowed. Analysts now projected the most likely entry path over the eastern Indian Ocean, with potential impact zones spanning the waters west of Sumatra to as far as the Coral Sea. The room fell silent as Dr. Elena Martinez, whose discovery had set everything in motion, presented the most recent data. QN1's radar returns from U.S. and European ground stations continued to show unusually low rotation, a reflective surface consistent with metallic composition, and no fragmentation yet. "We're looking at something solid, dense, and stable," she explained. "If it explodes in the atmosphere, it will be high energy. If it survives to impact, it's going to be devastating." A U.S. Air Force analyst interjected. "And the secondary object? What's the latest?" The response was unsettling. The smaller body, provisionally named 2027 QN2, had grown brighter over successive nights, suggesting it was rotating irregularly and possibly tumbling. Its orbit remained close behind QN1, raising the specter of two impacts in quick succession, potentially minutes apart. This was not part of any public statement. Around the world, governments were quietly mobilizing. In Indonesia, Australia, and parts of India, emergency management agencies initiated contingency drills under vague pretexts. Satellite reconnaissance systems were redirected to monitor the sky. U.S. and European early warning satellites were placed on high alert to ensure any infrared flash from atmospheric entry would be identified instantly, avoiding the risk of misinterpretation as a military launch. Publicly, officials struck a calm tone. Press conferences emphasized that impact was unlikely but being monitored closely. Privately, defense planners modeled worst-case scenarios. If QN1 exploded at low altitude, the resulting shockwave could flatten coastal infrastructure across hundreds of kilometers. If it reached the ocean intact, the tsunami risk was real. Even a 150-foot object, if dense and fast, could unleash energy equivalent to tens of megatons, rivaling mid-sized thermonuclear weapons. Meanwhile, public speculation was spiraling. The data leak had already fueled conspiracy theories, but the discovery of QN2 accelerated online chatter. Social media flooded with amateur orbital simulations, some accurate, others wildly exaggerated. One viral video falsely claimed the object was steering itself. Another misinterpreted radar data as evidence of artificial propulsion. Scientific organizations scrambled to provide clear, accessible explanations, but their carefully worded statements were drowned out by sensationalism. Hashtags like #Skyfall2027 and #QN1 Event trended globally. In some coastal cities along the projected corridor, rumors of secret evacuation orders triggered runs on fuel and food supplies. In response, the United Nations scheduled an emergency session of the Committee on the Peaceful Uses of Outer Space. For the first time, planetary defense was treated with the same diplomatic weight as nuclear arms control. Delegates debated whether any nation should attempt a last-minute interception. The consensus, with only days left, no known kinetic deflection technology could alter QN1's trajectory safely. Even a nuclear detonation would likely come too late and risk fragmenting the asteroid, potentially creating multiple impactors. But in a secure facility in Nevada, a small team of engineers and military officials was exploring something different. A classified experimental laser ablation system mounted on a high-altitude aircraft. The system, designed to heat and slightly nudge small objects during atmospheric entry, had never been tested against a real asteroid. Its potential to shift QN1's trajectory even by a fraction of a degree was uncertain. The mission, codenamed Project Zephyr, was controversial. If it failed, or worse, altered the trajectory unpredictably, it could shift the impact zone toward populated areas. Then came the turning point. On September 2nd, less than 4 days before QN1's closest approach, the Rubin Observatory detected a third faint object, QN3, moving on a nearly parallel trajectory, though further behind. Its size was estimated at 50 to 80 feet. This was no isolated rock. Earth was clearly intersecting a concentrated debris filament, most likely from the Taurid swarm. Dr. Martinez addressed the International Task Force with grim clarity. We are not looking at a single impact scenario. This is a cluster event. QN1 is the largest, but QN2 and QN3 are real, and we have no guarantee that there aren't more trailing behind. The room fell silent again, not with surprise, but with the weight of realization. The world was not facing a single cinematic doomsday rock. It was facing a wave, arriving on a fixed schedule set by orbital mechanics. The escalation was no longer theoretical. It was underway. Part 14 Countdown. September 4th, 2027. 22 hours before closest approach. At the Vera C. Rubin Observatory, Dr. Elena Martinez stood over a wall of real-time sky tracking displays. Outside, the Atacama Desert was silent and cold, but inside the control room, the atmosphere vibrated with quiet urgency. QN1 had crossed the orbit of the moon. Its faint point of light on the monitors was now brightening rapidly, exactly as predicted for an object on a shallow, stable entry path. The latest orbital refinement gave a 36% probability of impact, the highest yet, and the uncertainty corridor had narrowed to a brutal ribbon slicing across the eastern Indian Ocean. The world was watching. International Coordination Centers, Geneva. At the United Nations' newly formed Global Near-Earth Object Coordination Center in Geneva, diplomats, scientists, and military representatives from 47 nations were locked in marathon sessions. Every hour brought new data. The room was a surreal mix of urgency and protocol. One wall dominated by orbital simulations, another by simultaneous translations in a dozen languages. A decision point had been reached. Project Zephyr, the experimental laser ablation mission, had been approved for a limited attempt. 2 specially modified high-altitude aircraft were already being prepped at a classified airbase in Nevada. Their task: intercept QN1's atmospheric trajectory at the very edge of space, minutes before peak heating, and attempt to nudge its path upward by fractions of a degree. It was a gamble. If it worked, QN1 might explode higher in the atmosphere, dramatically reducing the shockwave. If it failed, the attempt could either do nothing or destabilize the object's structure in unpredictable ways. "We're not deflecting a bullet," one mission planner said. "We're trying to blow on a cannonball." The diplomatic stakes were just as high. Any action taken by a single nation, even under UN authorization, carried political risk. Several countries along the projected corridor had quietly requested full evacuation support, but moving millions on short notice was logistically impossible. Coastal cities from Chennai to Perth braced for impact as emergency drills shifted into actual emergency mode. Airports rerouted flights, ports cleared shipping lanes, and thousands of fishing boats in the Indian Ocean were ordered to return to shore. Media and public response. Across the globe, every major news network had switched to round-the-clock coverage. In Jakarta, crowds gathered in public squares, staring at giant screens replaying NASA's animations of possible impact scenarios. In Sydney, supermarkets were stripped bare within hours. Social media became a torrent of speculation, misinformation, and raw fear. Amateur astronomers streamed live telescope feeds, tracking the brightening speck that now represented a tangible threat. For many, the psychological impact was immediate and visceral. The idea of the sky falling had always belonged to myths, movies, or distant geological epochs. Now it had a date, a trajectory, and a countdown clock. Scientific teams, Pasadena and Darmstadt. At NASA's CNEOS Center in Pasadena and ESA's NEO Coordination Center in Darmstadt, teams of orbital dynamicists worked in synchronized shifts, feeding new data into predictive models every 15 minutes. Their goal: refine the trajectory enough to narrow the impact probability corridor to within tens of kilometers. They had managed to track QN2 and QN3 as well. QN2, the smaller trailing object, exhibited unstable rotation and a slight drift, suggesting it might fragment on entry, producing multiple airbursts rather than a single explosion. QN3, further behind, appeared more erratic, as if tumbling end over end. None of them were large enough to end civilization, but all were large enough to kill. The growing fear was that even a near miss could be catastrophic. If QN1 exploded lower than expected, a shockwave over a major city could kill hundreds of thousands. If it struck the ocean at the wrong angle, tsunami models showed waves radiating across the Indian Ocean basin within hours, impacting coastlines from Sri Lanka to Western Australia. T10 hours, a twist. At 3:17 Universal Time Coordinated, radar stations on Diego Garcia picked up something unexpected. QN1's radar cross-section had increased, almost doubling in strength over a 6-hour window. Initial panic suggested fragmentation, but the optical light curve told a different story. The object hadn't broken apart. Instead, it was rolling, exposing a previously unseen reflective surface. The new data forced a full recalculation of its shape and structure. QN1 was likely elongated, perhaps a metallic shard or monolithic fragment, rotating along its long axis. This meant its aerodynamic behavior during entry could be unpredictable. A small shift in its orientation could change its breakup altitude by tens of kilometers. The Project Zephyr mission planners were forced to rewrite their intercept profiles. The laser ablation attempt now had to contend not just with speed and distance, but with a tumbling target whose spin could alter every second. Some in the command chain argued to abort. Others insisted it was humanity's only chance to influence the event. T2 hours. Final briefings. Global attention focused on Geneva, where the UN Coordination Center held its final pre-approach briefing. Dr. Martinez addressed the assembly via live feed from Chile. This object is not civilization ending, but it is city ending, and the corridor runs through regions where hundreds of millions live. QN1 will not be stopped. At best, it can be slightly altered. At worst, we observe and respond. But we are now past the point of speculation. This is real. Military satellites were switched to continuous monitoring. Emergency broadcast systems in at-risk regions were placed on standby. Hospitals prepared for mass casualty events. Naval forces moved to open waters to avoid harbor damage. And then the skies over Nevada opened. The Zephyr aircraft launched under radio silence, climbing into the stratosphere, carrying technology never before tested in a real encounter. They were the thin line between calculated risk and unmitigated disaster. T0 approaching. As the world held its breath, telescopes began to register the first hints of atmospheric interaction. Faint ionization trails, whispering through the upper layers above the Indian Ocean. QN1 was arriving exactly on schedule. Its long metallic body caught the morning sunlight, flaring briefly, a distant, brilliant spark against the void. Every screen, every radar, every human gaze turned skyward. The countdown had reached 0. Part 15 Impact. September 4, 2027. 15:08 Universal Time Coordinated. The first visible flash came from above the eastern Indian Ocean, roughly 500 kilometers west of Sumatra. For less than half a second, it appeared as a brilliant star. Then it blossomed into something far greater. At an altitude of 38 kilometers, QN1 encountered the dense upper atmosphere. The object, now confirmed to be a metallic fragment roughly 140 feet long, began to glow incandescent white. High-resolution satellite imagery showed the leading edge shearing against atmospheric pressure, producing a shockwave cone that intensified as it descended. Its slow rotation caused alternating flares, like a tumbling mirror reflecting sunlight into space. Project Zephyr had made its attempt just minutes earlier. 2 high-altitude aircraft, operating near the stratospheric limit, had trained powerful laser arrays on QN1 as it crossed their firing window. The laser energy, delivered in short pulses, struck the asteroid's surface for a total of 21 seconds. Tracking radars recorded a measurable, but small alteration in its orientation, just under 0.05 degrees. It wasn't enough to change the trajectory dramatically, but it was enough to shift the breakup altitude upward by several kilometers. That difference would save tens of thousands of lives. Atmospheric entry. At 15:09 Universal Time Coordinated, QN1 underwent catastrophic structural failure at approximately 31 kilometers altitude. The metal-rich body fragmented violently, releasing energy equivalent to 26 megatons of TNT, roughly 1,500 times the Hiroshima bomb. The explosion produced a blinding flash, visible across Indonesia, Western Australia, and parts of the Indian Ocean basin. For nearly 30 seconds, the upper atmosphere lit up like a second sun. In coastal cities such as Banda Aceh, Padang, and Perth, windows shattered in concentric rings as shockwaves rolled outward. In Sumatra, seismographs recorded the blast as if it were an earthquake. Aircraft hundreds of miles away reported instrument fluctuations as the expanding plasma plume distorted radio signals. A ring-shaped cloud, the classic signature of a high-altitude airburst, formed and expanded rapidly, drifting eastward on prevailing winds. The Zephyr mission hadn't stopped QN1, but it had pushed the explosion higher than most models had anticipated. Instead of detonating in the lower atmosphere, where destruction on the ground would have been catastrophic, the blast occurred high enough that the shockwave was dispersed over a wider area, reducing overpressure at ground level. Still, the damage was severe. Across parts of western Indonesia, tens of thousands of buildings were damaged. Hospitals in Banda Aceh and Medan reported over 12,000 injuries, mostly from flying glass and structural collapses. Power grids flickered as substations tripped offline from electromagnetic interference. But no major cities were obliterated. The difference between a 26 megaton blast at 31 kilometers and at 18 kilometers had been the difference between a regional catastrophe and a mass casualty disaster. QN2 and QN3. Barely 20 minutes later, the world held its breath again as QN2 entered the atmosphere. Smaller and less stable, it broke apart high above the Bay of Bengal, producing multiple flashes between 45 and 30 kilometers altitude. The combined energy release was equivalent to roughly 3 megatons, distributed among several fragments. Though bright and spectacular, the explosions caused minimal ground damage. Shockwaves were felt in parts of southern India, but casualties were limited to minor injuries from broken glass. Several hours later, QN3, the smallest of the trio, disintegrated harmlessly over the open Pacific, its light show captured by satellite and shipboard observers. There were no impacts, no craters, only brilliant atmospheric scars fading into night. Immediate aftermath. Within minutes of QN1's explosion, emergency services across Indonesia, India, and Australia activated their impact response protocols. Naval vessels deployed to assess potential tsunami effects. None significant were detected, thanks to the mid-air detonation. Satellite constellations were temporarily disrupted by ionization effects in the upper atmosphere, causing brief navigation glitches and communications dropouts. International media called it the day the sky broke open. Live streams showed mushrooming atmospheric plumes, shattered skylines, and stunned survivors emerging from buildings. People described seeing a sunrise at noon, followed by rolling thunder that arrived minutes later. Social media feeds were overwhelmed with videos of the flash, some showing secondary reflections bouncing off high-rise towers like mirrors focusing light. In Geneva, the Global NEO Coordination Center confirmed within an hour. The QN1 object has disintegrated in the upper atmosphere. There is no surface impact. Emergency protocols remain active. QN2 and QN3 have also disintegrated without ground strikes. Cheers erupted in some control rooms. Others simply sat in silence, absorbing the magnitude of what had just happened. Geopolitical shockwaves. The political consequences were immediate. Leaders across the world issued emergency addresses. In Jakarta, the president appeared live on national television, visibly shaken but resolute. Today, the heavens reminded us of their power, but humanity stood together. We saw it coming, we acted, and we endured. In Washington, Geneva, and Moscow, analysts dissected the Zephyr mission's partial success. Though controversial, it was now undeniable that a coordinated, last-minute technological response had altered the outcome, not perfectly but measurably. The debate over whether to militarize asteroid defense, previously theoretical, now surged to the forefront of international politics. Scientific response. For scientists, the QN1 event was a treasure trove of data. Dozens of telescopes, satellites, and infrasound networks captured every phase of entry and explosion. The slow rotation, metallic composition, and clustered trajectory through the Taurid filament would fuel research for decades. Perhaps the most striking revelation came from post-event analysis. Radar backtracking indicated that at least 5 additional objects in the filament had passed behind QN3, all smaller, none threatening. Earth had, in effect, flown through the tip of a debris spear, emerging with bruises but intact. For the first time in human history, a multi-object swarm had been detected, tracked, and at least partially mitigated in real time. The sky had struck again. This time, humanity had seen it coming, and just barely held the line. Part 16, Aftermath and the Open Sky. For days after the QN1 airburst, the skies over the Indian Ocean remained streaked with pale vapor trails, curling like ribbons against the blue. Satellites continued to register elevated ionization in the upper atmosphere, while distant infrasound waves circled the globe, bouncing between hemispheres like echoes in a cathedral. Humanity had witnessed, measured, and survived a cosmic strike in real time. But survival came with consequences. The immediate world. Indonesia was the hardest hit. Along the Sumatran coast, thousands of buildings bore the scars of the shockwave. Collapsed walls, shattered glass, twisted steel. Emergency crews from more than 20 countries poured into the region, delivering supplies and expertise. Hospitals overflowed but did not collapse. Power grids were damaged, yet recoverable. Aerial imagery revealed the scale of the blast. Entire forests flattened in radial patterns beneath the upper air explosion, eerily reminiscent of Tunguska more than a century earlier. In India and Australia, the aftershocks were psychological rather than physical. People had watched the sky brighten at midday, felt their windows rattle minutes later, and known, instinctively, that something larger than nations had just happened. Religious leaders held mass vigils. Social media filled with shaky cell phone videos of the blinding flash, overlaid with timestamps and whispered prayers. For weeks afterward, nighttime skies were brighter across much of the southern hemisphere as high-altitude aerosols reflected sunlight, creating faint halos at twilight. Astronomers compared the effect to volcanic eruptions, except this time the trigger came from above, not below. Science rewritten. In the scientific community, the QN1 event was a watershed. The data gathered from optical telescopes, radar systems, infrasound detectors, and classified military sensors formed the most complete record of an asteroid airburst in human history. For the first time, researchers had tracked a cluster of multiple objects, analyzed their compositions in near real time, and observed the atmospheric effects of a megaton-scale explosion from start to finish. One of the most important findings came from spectral analysis. QN1's surface reflected unusually clean metallic signatures, unlike any previously catalogued asteroid of its size. It appeared to be a monolithic iron-nickel fragment, possibly a relic of a much larger parent body that broke apart millennia ago. QN2 and QN3, by contrast, were more typical stony bodies, further evidence that Earth had flown through a heterogeneous debris filament, not a single object. This event validated decades of theories about the Taurid complex, cometary breakups, and clustered impacts. It also revealed how narrow Earth's observational margin truly was. QN1 was discovered only 10 days before arrival. QN2 and QN3 followed even closer. The next swarm could contain dozens more. Policy and power. In Geneva, the UN emergency session on planetary defense extended for weeks. What had once been a subject of niche committees now commanded global attention. Delegates drafted the Geneva Protocol on Near-Earth Object Threats, a framework defining international authority for detection, information sharing, and emergency response. For the first time, a coordinated global chain of command for asteroid defense began to take shape. Project Zephyr, once a classified experiment, was now front-page news. Though imperfect, its role in raising the explosion altitude by several kilometers was undeniable. Nations debated whether to expand such technologies into a permanent rapid response system, and whether to place them under civilian or military control. The line between planetary defense and strategic weaponry grew thin, and not everyone trusted that line to hold. The political ripples reached far beyond defense policy. Stock markets initially plunged, then rebounded as damage estimates stabilized. Insurance firms scrambled to rewrite global risk models. Public trust in scientific institutions surged briefly, then fractured under the weight of conspiracy theories and misinformation that persisted despite the clear evidence. Humanity had witnessed the cosmos' power, but not everyone agreed on what it meant. A shift in perspective. For ordinary people, the QN1 event left a mark that went beyond statistics and treaties. Across cultures, the night sky became personal again. Children in Jakarta drew pictures of the second sun. In India, temples and mosques held shared prayers under the stars. In Perth, thousands gathered on beaches at sunset, watching the high-altitude wisps fade, speaking quietly of what could have been. For many, it was the first time the cosmos had felt real, not as distant stars, but as an active, unpredictable presence. Scientists noticed an unexpected surge of volunteers joining amateur astronomy networks. Telescope sales spiked worldwide. University programs in planetary science saw unprecedented enrollment. Humanity, it seemed, was looking up not just with fear but with focus. The questions that remain. Even as cleanup continued and data poured in, unanswered questions lingered. Where exactly did QN1 originate? How dense was the Taurid filament still trailing behind Earth's orbit? Were there other clusters waiting, unseen, in the glare of the sun or the darkness beyond? Radar backtracking suggested at least 3 additional small objects in the same filament had passed Earth days later, undetected until they were already receding. They were harmless this time, but the thought hung heavy. Next time they might not be. And then there was the timing. Orbital models indicated that Earth would cross the Taurid stream again in 2032, 5 years from now. No one could say whether another swarm awaited. But this time, humanity would watch the sky differently. In the Chilean desert, Dr. Elena Martinez stood alone outside the Rubin Observatory on a cold, silent night. Above her, the stars were sharper than ever, their light cutting through the thin air. She thought about how 10 days of data had changed the course of human history, how a handful of pixels on a monitor had become the hinge of a global event. She whispered, not to anyone in particular, "We saw it coming. We got lucky. Next time we have to be ready." Above her, the stars continued their silent motion, calm, indifferent, and patient. The sky had spoken. The question was whether humanity had truly listened.